Hello. Okay, we're going to continue on with chapter 17, plane motion of rigid bodies. And for this video, we're up to impulse and momentum. So this is for problems where we have velocities are changing and we're given information of force acting through a time period. So going back to F equals ma, this is where we're leaving a as dv dt. We take the dt over, so we have f dt, which is an impulse. Usually this happens through a very short time period, and this impulse will change the mv, the linear momentum of the object. As well as linear momentum, we can also look at moments and angular momentum. So if we just put r cross ma and do the same thing, so we bring the dt over, so we can have a moment acting through some kind of a time period and look at how that changes our r cross mv, our angular momentum. For some of these problems, we're going to have like conservation of angular momentum. You can think of an ice skater pulling her arms in. So initial r cross mv versus final r cross mv, so you change your radius. We'll play around with how you define your system boundaries, so you can look at internal versus external forces for solving problems. So quite a lot of possibilities here, but we're back into the world of vectors. So we're going to be splitting things into XYZ components. The linear momentum mv in the x direction is going to be changed by the forces in the x direction. Momentum in the y direction changed by the forces in the y direction. Our angular momentum, so in 2D, this will all be happening in the k direction coming out of the board. It'll almost feel a little bit like statics, where in statics you added the forces in the x direction and the forces in the y direction, and then you added the moments together. You had those three equations, three unknowns in 2D. And for this case, then you can look at linear momentum in the x direction and linear momentum in the y direction and the angular momentum around the k direction. So you can have kind of three equations, three unknowns to solve for problems. So we'll just go through some of the basic concepts in this video, and then the next videos will cover some examples that are going through applying these equations to some different scenarios. This is the other way to group problems. So again, we're looking at a system where velocities are changing from the start to the end. And this could be translational velocity, so something traveling in a straight line, or this could be looking at changing rotational velocities. So looking again at impulse, f dt, and moment dt. So anytime you get a problem statement that has force happening through time, or maybe there is no external force or external moment, in which case we'll look at conservation of linear and angular momentum. So that's another application for it. So here's some examples: a baseball, pool. This is going to remind you of chapter 14, systems of particles. So you can go back and review some of those chapter 14 notes if you would like, and then realize that all of these little collisions are happening very quickly. So we have FDT, very quick impulse. For these equations, so you notice we have three main terms through here. So we have the initial linear momentum of the system, and this could be looking at just a single particle or a bunch of particles, depending on how you define your system boundaries. But it's a good idea for all of these cases to draw pictures of each term in these equations. So if you look at the starting momentum, and this could be the starting MVs for each little particle in your system, and then think about what forces are acting on the system to change that momentum. And again, this is going to be external forces. So depending on how you define your system boundaries, that's going to control what forces are external versus internal to the system. And then at the very end, think about what is the final state of all the particles in your system. So for each piece of this equation, draw a picture of it so you can visualize starting velocities, forces that change it, and ending velocities. This is a vector, so the pictures will help you split everything up into X, Y, Z components and make sure you're not missing any of the forces that are going to be changing what's happening. So just like statics, when you draw free body diagrams for forces and to figure out what moments are, draw the initial rotation of it, what moments will change that rotation, and the final rotation of it. So angular velocities as well as linear velocities. And say it again, draw pictures of this thing. It's really going to help you keep track of everything. Okay, so let's look at equivalent systems. And again, this is going to feel like chapter 14. If I have a bunch of pool balls on a pool table or something, and I want to draw my system boundary around all of those together, what I can do is simplify it into just the linear momentum of the center of the system, so the center of gravity, and the rotation about the center. So I can take the individual masses and velocities of each particle, m1v1 plus m2v2 plus m3v3, and just add them all together. So here's a big summation sign, right? So we're adding each individual little piece of the system up, and we're replacing all of these complicated little vectors with the mass of the entire thing. So this would be m1 plus m2 plus m3 plus m4. So the entire mass. And if you add this all together, it gives you the velocity of the center of the system. So if you think of, like, I don't know, a swarm of bees or something, and you can think about each individual little bee in that swarm and what their individual masses and velocities are. Or if you're standing at a distance and you kind of blur your eyes and it looks like just one big mass and you can see the velocity of the entire swarm all together, that would be the simplified version where you're saying the linear momentum of the system is the entire mass all added together and the velocity of the center of gravity. And so you just add it all together. So don't let large systems of particles be intimidating to you. You just add it all together, and you can treat it just like one giant clump where you keep track of the center of gravity of that clump. The important thing there is to define your system boundaries very clearly and keep track of what crosses those boundaries. So as long as you keep everything inside of that boundary, you're good to go. So that the entire system as a whole will have some kind of linear momentum. It will also have an angular momentum. So you can, and generally you'll calculate this as a function of how everything is rotating around the center of gravity of it. Every now and then you'll find a system where you're taking the angular momentum around another point, but finding where the center of it is and then looking at where all the particles are with respect to the center. So this r cross mv, the r, goes from the center of the system to each individual particle when you're calculating the summation of these r cross mv. So you have the mass of each particle and velocity of each particle just like you did before, but this time you're going to add in that r cross mv where r goes from the center of gravity to each individual particle, and you're going to add up all those r cross mv's. Again, this is a cross product. So you are dividing your velocities up into x, y, z components. You're dividing your radiuses up into x, y, z components. Your angular velocity also will have x, y, z components. In 2D, all of the angular velocities will be around the k direction. So remember, it's describing the axis of rotation. So you're going to use that right-hand rule, and that defines your angular velocity. Okay, when you look at velocity is equal to r omega for rotational motion, and velocity is tangent to that. So that cross product works very easily with velocity because it's already 90 degrees to your radius. So you end up with an r squared m, and that r squared m turns into your inertia. So instead of mass times velocity, you have I times angular velocity. And your moment of inertia really does act like a mass. So the larger the mass, the larger your linear momentum, the larger your inertia, the larger your angular momentum. So it's kind of a, once you get that momentum going, how hard is it to stop, or how hard is it to get it going? So a larger mass is harder to kind of push and change that MV. A larger inertia is harder to rotate. So really think of inertia in the same way that you think of mass. It's a resistance to velocity, a resistance to acceleration. The larger your inertia is, the harder it is to get that angular acceleration going. Okay, so impulse momentum diagrams. Again, there's 3 parts to this equation, and we're going to draw a diagram for each piece of it. So we have velocities that are happening in x and y directions, and we also have rotational motion that is happening. For a system of particles, remember we can take all of those masses and velocities and rotations and add them all together and get just the big picture understanding of it, of what the center of mass is doing. So the velocity of the center of mass and all of the masses, and the system really does act like all of the particles are concentrated at that one point. It's kind of an interesting phenomenon. So you're looking at rotation around the center of mass and the velocity of the center of mass. Then to see what is going to change that, if there's any external forces to the system. And again, how you change your system boundary is going to determine what is external and what is internal. Internal forces are equal and opposite pairs and cancel out to one another. So anything that crosses the system boundary will have the impulsive forces. Sometimes, like if you have your mg, your weight forces, the impulse is generally a lot bigger than your weight forces. So you'll see those just ignored because of the order of magnitude. Like if you're hitting a baseball, the force between the bat and the baseball is huge compared to like the weight of the baseball. So you can ignore some of those smaller forces, but you're mainly concerned with kind of big external forces that are driving the system. And then after that external force happens, the external moment, so I can take R cross MA for each of these forces, and I can look at all of the moments happening in the system too that would create some kind of rotation at the end of it. So draw diagrams of each piece of these equations to look at what's happening at the start, what changes the rotation, what changes the linear momentum, and the final state of the system. And this will help you break everything up into X, Y, Z components. And in 2D, it's going to be 3 equations, 3 unknowns kind of a deal. So remember in statics, you looked at forces in the X direction, forces in the Y direction, moments. And this is going to feel a little bit like that. So you look at everything, the X direction, the Y direction, and then the rotational, the angular momentum, and the moments. Okay, so 3 equations, 3 unknowns for this, and draw pictures for all of it. Here is just an example to think through. So we have some kind of a bar, we have a ball that's heading towards it, and we want to draw the diagrams for what is happening here. For this, it's going to happen over a very short time period. So immediately before and immediately after. We're not going to worry about the bar swinging all the way up. So it's just right before and right after. So you're not even seeing too much of a difference of position in this. But before and after, you're going to have different velocities from this. And then like if the bar swings up or something, then you tack on an energy balance equation at the end of it to solve it. But for now, we'll look at just the impulse momentum piece of the problem, which happens over a very short time period. So very quick impact right before the impact, right after the impact. And again, we're looking at these 3 equations. So for this system, and there's a couple different ways you can divide this up. You can look at the ball and this bar together, or you can separate it. Maybe you want to know what impulsive force happened between the 2 things. So if I want to know what that force was, I'm going to have to use a smaller system. So if I just look at the ball, right, I'm ignoring this bar for a second. I'm just looking at the ball. So I have the starting velocity of the ball coming in right before it slams in. And then during the contact, the bar is going to be impacting the ball going to the left. And this will happen over a short time period. And then after the fact, you're going to have some new velocity. And this velocity could be to the right, it could be to the left. If you don't know what direction it's going, draw it in the positive direction just by default, and the math will work its way out to turn this into a negative or positive velocity. Some things to notice here when you're writing equations: there is a little tick mark on the velocity coming out of here. So you can either say v2 at time t2, or you put a tick mark above it to say this is a velocity after the impact. So make sure you get a labeling system that you can really understand and keep track of all of your different variables in this. So initial velocity, impact, and final velocity. And those are the three pieces of this equation. Once you have the ball, now we can look at this bar. So for the bar, initially it's just hanging there. It's not doing anything. So we can say mv is 0, I omega is 0. The ball, it's kind of a particle. So for the ball, we didn't worry about our moment or our angular momentum. But for this bar, before and after, it's going to be rotating. So we're going to have to keep track of this second equation as well as the first equation for the bar. So initially, everything is 0. We don't have to worry about it. For the forces, and again, this impact force is probably going to be huge compared to the weight of the thing. So you can decide whether to add in the weight hanging down or not, and maybe you can calculate it both ways and see the order of magnitude there for if this force needs to be included or not. But I mean, to be really accurate, then we can draw on the weight of it. Okay, so we have a pin. Make sure you don't forget to add forces for anywhere it's connected to the outside world. So if we're isolating this bar, then anything it touches, there's going to be a force there, and then gravity that also goes across into the boundary. So this is kind of this middle term of the equation. So we're looking at both the force, F dt, and we're going to be looking at the moment, dt. And we can decide what point would be best to take the moment around, if we're going to leave that around the center of gravity, or maybe for this one, it would be better to take the moment around point A. Because if you take the moment around point A, you don't have to worry about the forces at A, so it's a lot easier. And it's just like statics. So if you go back to statics, you could take the moment around any point on that system. Same thing for this angular momentum and moment. You can take the angular momentum and the moment around any point on there, and generally it'll give you a much simpler equation if you take that moment around a point where there's a bunch of unknowns. Because if I take it around A, I don't have to worry about AX or AY. Those are not rotating it around A, so it makes it for a simpler equation to solve. Okay, the final system, and these kinetic diagrams at the end are all going to look pretty much the same. You're going to have some kind of an MV in the X direction. This case, there's nothing happening in the Y direction and some sort of rotation. So you can always start with that same group all attached to the center of gravity of the system. And for particles, you don't have to worry about rotation. It's not moving in the Y direction, so it's a very simple MV, but you're always going to just attach this to the center of gravity. So this final system, it'll always look kind of the same for that. Okay, fixed axis rotation. So this is where you have one piece of it that's fixed in place. This is kind of the generic potato model. So this could be a rod, it could be anything that is stuck in place. And from this rotation, so it's rotating around the end here, and we're still going to keep track of what the center of it is doing. So the velocity of the center here is going to be some kind of r times omega. And then you can also look at the inertia around the center, because generally tables are going to give you the moment of inertia around the center of the object. And this is another case where, remember back to the parallel axis theorem. So if you're rotating around an axis that is not the center of mass, the inertia around that new axis is equal to what it is around the center plus md squared, where d is just the distance from the new axis of rotation to the center of gravity. And you can go back and forth between those. So if you do happen to know the inertia around this new axis of rotation, then that's all you need. You can say I omega. But if you don't know what the inertia is around this new axis, if you only have what it is around the center of mass, which is what you generally see in tables, then you have to have both of these terms. You have to have I omega inertia around the center, and you have to know the velocity of the center, which is just r omega. So use this parallel axis theorem, and one way or the other, you can get the information you need. So these are equivalent to one another. I omega, if you know it around O, or if you just have what's happening to the center of gravity, you need both of those terms. And these two add together, of course, to what your initial inertia is. Okay, systems of particles versus individual particles. So if you have a bunch of particles all bouncing around, you can analyze them one by one and look at each individual ball before and after collisions, or you can add the whole thing together, just draw your system boundary around the entire group and just worry about external forces changing the overall motion of the center of gravity of the entire system. For all of those, you're going to attach MV to the center of gravity of the entire system, and it's just a summation sign above around all of this stuff. Okay, so let's look at an example, and we'll go back to the simple example that we're familiar with. So we had a ball and a bar, and you can consider just this one piece of it, or you can consider just this other piece of it, but realize that we have some equal and opposite forces going on here. So if instead of looking at each individual piece of it independently, we draw our system boundaries around the entire thing, we can get rid of all of these equal and opposite individual internal forces. So down here is the system together. So we're drawing our system boundary to include everything in here, the ball and the bar, in which case I'm not including these equal and opposite forces during the collision. So the only force that we have to worry about during a collision is the force at the pin A, which is external to the system. So we look at initially all of the MVs adding together, initially any rotations going on, and then any external forces to both of the particles in this case, and exiting out, we have another system of MVs and I omegas to the system. Okay, so conservation of linear momentum and angular momentum. This goes back to like an ice skater pulling their arms in. So depending on how you define your system, you can say maybe the ice is super slippery and there's no real external forces here. And what you have is a different inertia before and after she puts her arms in. So remember, inertia is like r squared m. It's very dependent on the radius. So if you have a very large radius, you're going to be spinning slowly. If you bring your arms in, small radius, small inertia means you're going to be rotating faster for this. You can also remember back to orbital mechanics and looking at the velocities of rotating planetary objects. And this r cross mv, remember v is r omega, so you get that r squared m, it turns into I omega. If I look at the velocity of the planet on one side versus the other side, this is another conservation of angular momentum because the gravitational forces are not perpendicular. It's not going to change that angular momentum of the system because of the cross product. So we can ignore mdt for central forces like gravity, and you can calculate the velocities at both sides of this orbit by looking at how the radius. So if you know the velocity at one side, you can figure out what the velocity at the other side. So that's another example of conservation of angular momentum. Okay, so the total linear momentum and angular momentum at any point are conserved. So that's if we can get rid of kind of these external forces or external moments, then you have the same initial and final. And this is usually used for systems of particles. So you have initially a bunch of MVs running around, and then they collide with one another, and maybe this is all internal forces that are equal and opposite. Then you have some final linear momentum. And the new piece to that from chapters gone by is adding the angular momentum conservation as well as the linear momentum. Okay, here's some concept questions. Is the angular momentum around G conserved? So let's look at point G here. So we're going to take everything around point G. What do you think? If I say R cross MV, this little guy right here, that means it's not conserved around point G. Bummer. Okay, how about, is angular momentum conserved around point A? So let's think about point A this time around. So initially, we have some kind of an R cross MV, and then it's going to change, and now we have some new R cross MV. Do we have anything in the middle? So do we have any kind of a moment dt changing it? Well, because these two forces go through point A, there's no moment around point A that is changing it. Remember, for the entire system, this is equal and opposite forces. They cancel out. So in this case, if I take moments and angular momentums around point A, then yes, it's conserved because I don't have any MDT. I don't have any impulse around point A. Okay, is the linear momentum of the entire system conserved? So what do you think? The entire thing, is this conserved? And this is looking at MV plus FDT equals MV. So is there any kind of FDTs going on in this system? Well, yes, there is. There's these external forces because of the pin at A, and so we'd have to say that no, the entire system is not conserved. So you can see that you can play these games with angular momentum by what point you take that angular momentum around to get things that are conserved, which can really help out in a lot of problems when you're solving for them. I'll save the example problems for later.